might be.
Thank you for that. Yes, well done. Our next talk is going to be by Coralie Siegel, who has been waiting patiently. She's going to talk about, surprise, Century, reaction path models and halo implications. Thanks, Coralie.
Thank you, Helen, and thank you for the opportunity. Okay. And for the opportunity to speak today. I'm going to present some work I have done at Century, but coming from a different perspective. I want to look at the geochemical modeling and how we can use that for predicting halos and test hypotheses of R-forming processes. So this is some work I have done in collaboration with Yan Mei and Siegel, and that has been funded by the CSIRO Deep Earth Imaging Future Science Platform. So chemical reaction path modeling is a type of fluid-work interaction, and that is what I will be focusing on today. The idea for this type of modeling is to test hypotheses of R-forming processes and potentially and obviously predict a series of mineral alteration assemblages for a specific emplacement style. So in a nutshell, we consider a block of rock for which we have that we subdivide in discrete intervals. And we have a fluid infiltrating this block. And at each interval, we calculate the local chemical equilibrium, which is what we call a step flow through reactor model. As the fluid infiltrates the rock column, the fluid chemistry will change, the host rock will change, and obviously we will have different mineralogical assemblages. So on the right-hand side, just to a pointer here, on the right-hand side, we see different minerals that are color-coded, and we can observe different mineralogical assemblages. So that is the type of models that have been doing for Century. And the idea here is not to do a complex 3D model. It is really about trying to predict the hydrothermal footprint for a particular emplacement style. So this is a snapshot of one of those models, where as we infiltrate fluid upon entry on the left-hand side, we see the development of those different metasomatic zones. So the approach we're choosing is to first develop a conceptual geological model to then make some model predictions. So the first aspect is to review the existing data and come up with plausible scenarios that we want to test. We then want to identify, looking at the geochemistry, under what conditions the base metals are being carried in solution and under what conditions they get deposited. And then bringing those two aspects together, we then develop a geological conceptual model that we can test. We then infer from the results of this model, what are the parameters, the mineralogical or the geochemical proxies that we might be able to use for exploration. So diving into Century now, we chose this system because there is no metamorphic overprint, and therefore it is easier to reconcile the results of the geochemical models with the observed mineralogy. And then, there is also a wealth of existing data, including the temperature and the salinity of the fluids, which are critical for constraining the starting point of our models. So Century is located at the edge of the Thermite Trench Fault, which is believed to be the conduit of the fluid flow that drives the mineralization. To the south of the Thermite Trench Fault, we have other zinc-lead occurrences that are shown here in gray triangles, and we'll see them better in different maps later on. So mineralization is hosted in organic rich shells of the Lawn Hill Formation. And it consists essentially of sphalerite, minor galena, little pyrite, and rare chalcopyrite. There is also a significant lack of pyrite and a very strong sideritic signature. The previous studies have shown there is iron and manganese enrichment towards the ore body. And obviously, as Peter discussed before, there is still a debate about the origin of this deposit, whether it is syngenetic or whether it is a replacement style. I'll show it here that lead model ages suggest mineralization post-dated deposition by around 20 million years. But again, there is a debate about the validity of those ages. Century is subdivided into 4 units. What I want to show on this particular slide here is that there is a very strong siltstone shell alternation throughout the ore body that has been intercepted by 2 different drill core. And the key aspect here is that the shell horizon, as shown here in the 200 black unit, is enriched in zinc, in lead, but also in total organic carbon content. The siltstone horizons, however, are unmineralized, and they are enriched in iron, manganese. And so when we look a little bit closer at those rocks, we see a very intrinsic relationship between the organic matter and the sulfide mineralization. And this has been reported in the literature by the presence of porous sphalerite, and that consists of minute crystals of sphalerite within a sea of pyrobitumen. Further to this, we look at regional halide crystallinity, which basically measures the thermal maturity of the organic matter. And what we observe here is that halide crystallinity is relatively high to the south of the Termite Range fault, indicating the circulation of hot fluids that have interacted with the organic matter-rich rocks. Obviously, there's a degree of caution here because the spatial distribution of the data points is relatively scarce. However, there's a very strong polarity at the Termite Range fault. So now looking at the geochemistry, let's look at what conditions zinc gets carried in solution and deposited. So this is an activity diagram for zinc at about 3 mole of sodium chloride and at 200 degrees. It shows that zinc is being carried in solution as a chloride complex in oxidized environment, but also in reduced acidic fluid. And there are 2 mechanisms of deposition that are highlighted by those arrows. The first one, where we have an oxidized brine that undergo a very strong sulfate reduction by either thermochemical sulfate reduction or bacterial sulfate reduction. This is generally what we see in Macassar type or Montizer type deposits. And then we have a second process where we have a reduced acidic fluid that undergo a pH increase through buffering of the host rock. And that is what we would expect for a Selwyn type or Broken Hill type deposit. In regards to Century, there is a lack of barite, there is early zinc-rich carbonate, which both advocate for an oxidized fluid. And that is because barite, now I don't have it here, but I can show you later on if you're interested. Barite is insoluble in oxidized environment and therefore cannot be carried in a fluid, whereas in acidic reduced fluid, barite is soluble, can be carried in the fluid, and as a pH increase, it can then be deposited. The sulfur fractionation, so the sulfur isotopes fractionation of about 10–15% below the parental sulfate suggests that this reduction occurs by thermochemical sulfate reduction, and that occurs by the oxidation of hydrocarbons by sulfate as the oxidized fluid is interacting with the organic matter-rich rock. And this is the reaction that occurs and that also allows the precipitation of carbonates. And depending on the metal cations that are available at the time, then there is different carbonate types that might precipitate, such as siderite, anchorite, and dolomite. And that could be one of the reasons that we have also different halos, among other reasons. Bringing all this information and knowledge together, we then come up with a conceptual geological model we want to test. In this case, I'm using a replacement style scenario in which we have a meteoritic water that is driving through the below to the stratigraphic sequence, and there are key interactions that I'm talking about here that we want to test. The first one is the interaction of this fluid with an evaporite bearing sequence, which lead to an oxidized and highly saline fluid. That fluid then circulates through solidic basalt, which is believed to be the source of the base metal. And it is that interaction between that oxidized fluid and that basalt that allows the zinc and the lead to be carried in solution. We then have a metalliferous brine that is rising through the termite trench fault and then percolating through the carbonaceous shell, where the thermochemical sulfite reduction will trigger the precipitation of the base metal sulfide. So to test this scenario, we use HCH, and this is the model architecture we decided to take. So we have first the water interacting with the evaporite bearing sequence. We then take the resulting fluid composition, and we then pass it through a starting point for that chemical equilibrium calculated in that basalt block. We then take that resulting composition, which is basically the metalliferous brine, and then circulate that through the shell sequence. Now we've done two models. We've done one model where the host rock has organic matter, and the second one where the host rock has no organic matter. And the key aspect here was we wanted to test the role organic matter has for triggering base metal sulfide mineralization. So the results basically show that the metalliferous brine is oxidized, and when it interact with the host rock with organic matter, we become strongly reduced, and we have precipitation of sulfides such as sphalerite and galena. We also have the precipitation, predict the precipitation of siderite. However, when the metalliferous brine interact with the host rock without organic matter, the environment remains relatively oxidized, and therefore we do not precipitate those sulfides. So again, this is the carbonate and the sulfide mineralogy that we expect for those two different models. And what we see is for the carbonates, we predict the precipitation of iron and manganese-rich carbonate towards the ore body, towards the fault. So just some key takeaways here are our fieldwork interaction geochemical models indicate that the organic matter has a critical role in triggering base metal sulfide mineralization via the thermochemical sulfate reduction. The models predict the precipitation of iron and manganese-rich carbonates at proximity to zinc-lead mineralization, and that is consistent with what we observed at Century. And then the key takeaway I'd like to really for you to take is the fact that carbonates, iron, manganese, total organic carbon, and E-like crystallinity are, I believe, key exploration vectors, and that the coincident presence of organic matter and sulfide mineralization should not be overlooked. I think organic matter has a key role, and it shouldn't be overlooked. Thank you.
Thanks, Coralie. That was excellent, and definitely a different perspective. Organic carbon is a pretty good reductant. Mm. So we have a question regarding Walford Creek, and I think it came from Dan Johnson for Peter McGoldrick, but I think it also could tie into some of the work that Coralie was talking about, but we might save it for the discussion at the end.